we start the second day of this intensive workshop, as I was told by some students. I like them all. And the first speaker today is Uwe Jannsen from the University of Regensburg, and he is going to speak about weights and Hasse principles for high-dimensional arithmetic fields.
Okay, thank you very much, and thank you very much to all organizers for the invitation and the opportunity to speak here. So maybe sooner or later I will probably go to this space, so maybe I can switch this off. Is this okay? Well. Okay, so the title contains weights and also Hasse principles, and I found it best if I have some chalk. So if I maybe start with some preliminaries. So K is a global field, so either a number field or a global function field. Then you have the Brouwer-Hasse-Noether sequence. Exact sequence of Brouwer groups, which goes as follows. So we have the Brouwer group of K, and then you map to the Brouwer groups of all local fields. So these are the places of K, and these are the completions. And then you get an exact sequence as follows. So this is injective. So this injectivity is often called the Hasse principle, and you also understand the co-kernel. Now, also it's known that this can be expressed in terms of Galois cohomology. So I first write it down, H2K Galois cohomology Q mod Z1, and then same here. However, if we deal with the P primary component, where P is the characteristic, so in the global function field case, one has to pay attention to what this means. So notation, so if L is a field, and N is a natural number, and I is an integer, or maybe J, so then by definition Hi, L, Z mod N, J, so the so-called J-fold Tate twist of this, so is defined as follows. So you write N equal to M times P to the R, where P is the characteristic. So this doesn't exist here if characteristic is 0, and where P does not divide M. Okay? So you split off the P component, where P is the characteristic, and then it's the usual thing that's very familiar. So you take the mth root of unity and take its jth tensor power. And then for the P part, you do the following. You write Hi minus J, and here you take the logarithmic Diramovic. Sorry, so this is omega J L log, and then WR. So the so-called logarithmic Diramovic sheaf. And then one can show that the Brouwer group can also be written as this Galois cohomology. So maybe this is the best motivation to consider these sheaves, and we will encounter them again. And also, they appear in the so-called Milnor-Bloch-Kato conjecture, which I will need at a certain point. So, well, this is any field. This you can do for any field. Yeah, this is absolute. So if you write, you take the differentials over Fp. Yeah, yeah. So Milnor-Bloch-Kato conjecture, or simply Bloch-Kato conjecture for short, So, in fact, with this notation, you have a Galois symbol HT L. So L any prime could be the characteristic. Which goes from Milnor K theory, Milnor K theory, modulo L. So this is Milnor K theory, which is by definition the t-fold tensor product of the multiplicative group modulo the so-called Steinberg relation. Okay, so anyway, this is generated by tensors, so-called symbols, and then you have a map to the Galois cohomology HT L Z mod L T twist. And for L equals P, you take these logarithmic derivatives. And so this is just for T equals 1, this is Kummer theory or an analog for the P case, and then you take the cup product of the symbols. So the conjecture, Loch-Kato conjecture for L, T, and this prime L is that this is surjective. Okay, what is the status of this conjecture? So if L is equal to the characteristic, then this is okay. This is Bloch and Kato in the paper. So L different from the characteristic. Then there are several cases. So for T equals 1, this is the classical Kummer theory. T equals 2, it's a famous theorem due to Merkurjev-Suslin. In the other direction, if L, the prime, is equal to 2, this is also proved in all cases for all T by Wojewodsky. That was the original Milnor conjecture. And in general, this proof was announced by Rost and Wojewodsky. And people are working hard to make a write-up from the notes which exist by Rost and Wojewodsky. Okay, so anyway, I will tell when I want to assume this, this result. Okay, so now let me make the statement. Any field, yeah. I mean, there were early results by Tate for number fields and so on, but these proof always you look at general fields and then prove it for these degrees. Okay, so now the first theorem that I want to present . Where's the eraser? Not the eraser. Yeah, down. Yeah. Okay, thanks. So now we come to Hasse principles for functions field, for finitely generated function fields. Okay, so first theorem. So let K be a number field, and let F be a function field in D variables. Over K. Okay, so just the function field of a, let's say, geometrically irreducible variety over K. of dimension d. So let Fv be the corresponding function field over Kv, over the completion. Okay, so that means, so if say f is k of v for variety, then Fv is Kv of the variety base change to Kv. So as I said, I assume that it's geometrically irreducible maybe. Then hd plus 2 f q mod z d plus 1 hd plus 2, same things for the Fv. This is injective. Okay, so some remarks. So this was conjectured by Kato and proved by him for d equal 1. Conjectured by Kato, proved by him for d equals 1. Then I proved this already some time ago, and first for d equals 2 and then higher. And okay, so yeah, okay, so maybe I leave it as this. And the other comment is, so corresponding, if C is a curve over the number field, so a curve, smooth projective curve, and you consider f the function field of a curve, and say you have a k-rational point, then if you look at the Brauer groups again, this is not injective. So kernel of the Brauer group, first of all, does not go to the direct sum, but the product. This is canonically isomorphic to the Tate-Shafarevich group of the Jacobian of C. So this is non-trivial in general. So Brauer groups don't work. I mean, this was an insight of Kato. And then, of course, if you look at the classical, maybe this is the first remark. Classical is just the case d equals 0. So where you have H2 and the one twist. Okay, so this was the correct generalization. And the theorem 2 is the same holds and now here I should be a little bit careful. I think probably this can be done, but I mean in the moment I can only do this away from the characteristic. Over the function field, global function field, K, if resolution of singularities holds over K. I don't want to make this too precise, certain kind of resolution. And so, of course, the resolution in characteristic P is not known. And but there are some results in small dimension. Of course, for curve, it's no problem. But anyway, so again, proved by Kato, conjectured and proved for d equals 1. Not mentioning resolution, but okay. So unconditional.
So what does that mean away from characteristic?
Okay, so you can always write this as the sum of the L primary components, and then you have QL mod ZL, and I do not consider the L L equals P part. So unconditional for D at most 3 due to recent results on resolution of singularities. So this is a paper of Cossard and Pilton, which gives result for D equals 3 in a weak sense, so that the function field has a smooth projective model. And for D equals 2, exists a stronger result due to Cossard, myself, and Saito. So where you can find nice compactification of smooth varieties. So once you have this result, I mean, very nice resolution in dimension 2.
What is K? K is the function field of variety over F, where F is a global.
Right. No, K is FC, where this is a curve over a finite field. This is a global.
What is? No.
Yeah, here. Global function field is this. The global function field is a global field in the sense of André Weil. So function field in one variable over a finite field. And over this, I take an F function field of degree D.
The same refers to theorem 1 right now? When you say the same?
Yeah, the same as in theorem 1.
Sorry, and what were you saying right above that, about this curve and the chart? What's the relevance of that?
So that the formulation with this Galois cohomology is the correct one, and Brauer groups do not work for injectivity results. Yeah. Okay. So the method of corollary. So so I'm just if the Bloch-Kato conjecture holds, get the same for finite coefficients. Z mod n d plus 1 in both cases. And why is this so? I can do this here in this. Rather, I want to explain how this works. So if you have this Bloch-Kato conjecture, L, T, little l, then you easily deduce from this that Milnor K theory tensored with QL mod ZL surjects onto this Galois cohomology. Yeah? This implies by the mod L. This is standard deduction. And so in particular, this implies that this is divisible, because this is a divisible group. And this again implies by the long exact cohomology sequence that for any R, H t plus 1 L, Z modulo L to the R with a T twist embeds in this same version with the infinite coefficients. Given by the Kummer map, okay? Because here you would have HT with the T twist and these infinite coefficients, and also the L to the T power map, and so this is surjective here, and so you get the injectivity. So if you have this for the function field and also for the local function field, then from this injectivity here you deduce this one. Okay, so this is a well-known trick. And in fact, Kato proved his result it's not sort of separated so clearly in infinite coefficients and finite coefficients, but he used Merkurjev-Suslin for his result. Okay, now I want to discuss the technique of proof, and this goes via weights. And also
Sorry, this may be a silly question, but to get to these finite coefficients from these divisible coefficients, it really requires Bloch-Plateau?
yeah, I thought about this for such a long time, but I do not see any other way.
Very strange.
Yeah. It's, I cannot do it otherwise. And I think it's very reasonable to do it like this. So now I come to weights. So first, consider the LR case. So L different from the characteristic of the ground field. So let K be an arbitrary field, and K bar be the separable closure, and L different from the characteristic. So if you have a smooth projective variety X over K, so any variety of course, so then the Galois group, absolute Galois group, acts on the étale cohomology, so H n x bar QL, and this is the lift to, and this is of course just by functoriality, Galois group acting on K bar, functoriality of étale cohomology. And so first consider the case of a finite field, so K finite field. So K say FQ, field of Q elements. Q is P to the R, and so P is different from L. Then Deligne proved the Weyl conjectures by using weights. So then you have, so then Deligne proof of Weyl conjectures. Can be expressed in his situation that this is pure of weight n. So this means the eigenvalues for x proper and smooth. Thank you. It's important. So the eigenvalues of the geometric Frobenius Fr in this situation in GK alpha say are algebraic. So usually the characteristic polynomial is over QL, but it's actually a polynomial over QT. And one has sigma alpha absolute value is equal to Q n over 2 for all embeddings of Q alpha. So this is by the assumption that it's algebraic, so this is finite over Q, and you can embed it into C. So for all embeddings. Okay. So in general, if you are over a more general field, there's also a purity result. So case 2, K finitely generated, if you like, over the prime field, so finitely generated function field over the prime field, over Q or Q, Fp. Again, Hn, so for x smooth and proper, is again, it's a Galois representation and is again pure of weight n. What does it mean? So there exists, so here in this situation, there exists some scheme which is integral in a finite type over the integers, and with function field k, and there exists and in addition scheme over S, smooth and proper, such that this extends x over k, which is the generic fiber of this family. And then you have a base change isomorphism Hn x bar ql is isomorphic to Hn. So where this is the for all closed S in S. So where this is the base change to S, and you take again passage to the algebraic closure of the residue field of S, and note that the residue field K of S is finite for the closed point. So then on the right hand side we have the cohomology of a smooth proper variety over a finite field, and there we have these properties of the Frobenius eigenvalues, and also this this here is above is equivariant, so you have the decomposition group also in this general situation for finally general field decomposition group for S, and this is the inertia group. And then this isomorphism is equivariant for this action of the decomposition groups, and this means that IS externally on the left hand side, and so so in other words GS modulo IS, which is isomorphic to the Galois group of the finite residue field X, and here you have Frobenius, and then these eigenvalues are pure of weight n. So that's the definition, and this formalizes general notion of pure QL representation of GK, so of some weight, because you only say that you have this S here, you forget the whole rest, but you have this situation and you assume that the inertia for all S and S sufficient, some suitable S act trivial, and you have this purity of the Frobenius eigenvalues. Okay, and now the Pierre case is a little bit more subtle. So maybe so again, so P had a case. So P is equal to L, which is the characteristic of the field. So again, if two cases, so if K equal to if Q is finite, then you have the following. You have the crystalline cohomology x over w of k, and you can cancel this with q, and then it's a finitely generated vector space over the fraction field of the ring of bit vectors. Okay. So and then Katz and Messing have shown that this is again pure of weight n. This follows from Deline's proof of the Weil conjectures by some. Pardon? That is, yeah, here I should maybe then write this same k, right? Okay, and then for k finitely generated, then exists some s as above. So again, always here is x is smooth and proper, as above. And then by Gros and Suhr, not on this given S maybe, but there exists U in S, dense open, and base change isomorphism. Okay, sorry, I was going too fast. So from this here, sorry, okay, so this, I should go to the make a digression. So this crystalline cohomology is also HN Zariski et al. Cohomology of the de Rham-Witt sheaf. It's a pro system, omega x over k. So this is the de Rham-Witt complex. And now you have an exact sequence W dot, say, omega r. Okay. So so-called logarithmic part of the de Rham-Witt complex. And here W dot, maybe this I can omit here, W dot omega Rx, which is exact as a as an exact sequence of sheaves. And so this is the logarithmic de Rham-Witt. So on nth level, it's this omega n, which I used for fields already. And then from this, one deduces actually an exact sequence Hn x bar, so over the algebraic closure. And then here H1 Chris x over W, Q, and here the same. Where here is the Frobenius of the de Rham-Witt complex. And here still you have an action of the geometric Frobenius of the Gallo group. And from this, one also deduces by some semilinear algebra that this is pure of weight n. In fact, it collects the eigenvalues on the crystalline cohomology which have slope r. Okay? So in this sense, this is pure, but also this is pure here. With the same notation as before, first you take Zp, I mean the projective limit of what we had with the logarithmic de Rham-Witt complex, and then QP version. And then here you have a base change isomorphism Hn is p-adic QPR isomorphic to Hn xs bar QPR. This is not the base change isomorphism for the crystalline cohomology, but rather in this setting here. So then you play the same. It's also equivariant, and it's exactly also pure in the same sense as above. So for the S, for all S in U closed. So perhaps you have to shrink S, as I said, but then you have the same situation. Okay, purity. So what does it help, this purity? Well, I mean, still in this finitely generated situation. So note. So if V is a pure QLGK representation, finite dimensional, and of weight W, which is non-zero, then the fixed module is 0. Okay? Because if so for a finitely generated field, you can just go to any decomposition group as before, GS, and Frobenius X. And the Frobenius has these eigenvalues. And if the fixed module is non-zero, then there must be a Frobenius eigenvalue 1. But 1 has weight 0. Okay? So if the weight is not 0, you cannot have eigenvalue 1 for Frobenius. So already one single Frobenius element suffices to tell you that the fixed module is 0. Okay, so this is the application I have for the weights. Okay, so in fact, I come to the third section. So this gives a certain Hasse principle for Galois cohomology. Pardon? W is V. Yeah, too many. Sure. Thanks. Okay.
I'm sorry. So S is again finally generated over Z. That's what you
Yes, S above, exactly S above.
Well,
In this case, it would be finally generated over FP.
oh, here is FP. I see.
Yeah. I mean, I did not say that S even before. I mean, I didn't say that S needs to be flat over spec S, spec Z.
But here, I guess it has to be over FP.
Yeah, sure. So, okay, I will mention a conjecture and state a conjecture and a theorem. So, as before, K is a global field. And so, in the okay, so then I have a conjecture. So let K be a number field, and let U in spec of the ring of integers of K be open, non-empty. And let L be invertible, a prime, invertible on U. And let F be a smooth QL sheaf on U. Then the conjecture is the second Étale cohomology of F injects into okay, also for notation, I want to have S equal to spec OK minus U, so the missing places in S. So then I have H2 and the local fields, the completions. Then this is injective. If F is pure of weight W different from -1. Okay, I just want to mention this because I mean, some time ago I stated several vanishing conjectures on this type of cohomology. Actually, I mean, maybe, of course, this is just Galois cohomology. So the map is just H2 GS, where this is the Gallo group of the maximal S-ramified extension, and then you have just a representation of this group, which is pure, and so this is just this familiar map here. So, and if you exploit this conjecture, fun? Well, I assumed that L is invertible on the complement, so S must at least contain all the primes above L, as usual. Yeah. S cannot be empty. It implies earlier conjecture I had on vanishing, because then you go this
it
local.
could contain S could be only 1 point, right?
If there's only one prime above L,
One
yes.
kind of
Yes.
L. And then you say that this, for my completion, recognizes the whole cohomology?
Yes. This is my conjecture. And this is partly sort of motivated by a theorem, the analog holds over function fields, global function fields. So it's not a number field, but a global field of characteristic P. Okay, so I just want to mention this. But the theorem is the following. So if V is even a mixed QLGK representation of weights different from -2, and if A is something that you obtain by dividing out lattice, so it's something like QL mod ZL to some power, then you have an isomorphism. So I mean, so that means you may have mixed. I did not explain mixed. So this just means you have a filtration Wn on this, so that the graded pieces I, which is Wi V modulo Wi minus 1V, that this is pure of some weight. And the weights occurring are those on the graded pieces. So it's just a notion of the linear. So you have some filtration with pure quotients. So then you have an isomorphism. Perfect Hasse principle, H2, GKV, say, A. Okay. Okay, this is a longer story why this weights here should be not -2 and here -1, but maybe for lack of time I'll skip this. So this is this holds both in the function field case and the number field case. But note that this is not helpful for the Brauer group, because for the Brauer group we have the Tate twist 1, and maybe I should point out that note QL of I is pure of weight. And so this is by passing to the ZL of I from the previous definition and then tensor QL. So this is pure of weight -2I. So if this is 1, I exactly have the situation that this kind of Hasse principle does not hold. So, and it's known that there are representations of weight -2 where you do not have this isomorphism, you have some kernel. Okay. Good. Now I want to go to the proof of Hasse principle. Theorems 1 and 2. So the method is to use weights and the following. So if U is just any smooth, but not necessarily projective variety over K. So let's say this in general for a global field. So if you have resolution of singularities, so OK for characteristic K0 by Hironaka, but not known in general for characteristic P, there exists a good compactification. So U can be embedded in something which is smooth and proper. And the complement Y, which is X minus U, is a divisor with normal crossings. So, divisor with normal crossing, what does it mean? Down to earth terms. So, divisor with normal crossings. And maybe I just assume simple normal crossings. So that means the yi are smooth divisors. And the intersections are all smooth. The R-fold intersections, let's say Q-fold intersections. So Q-fold intersections for I1 smaller than I2 and so on. Different indices are smooth of dimension, so let's see, of dimension D, pure dimension D minus Q. So it is smooth and has the correct codimension. And then I form the disjoint union over all these tuples here. So this should go here. This is the explanation of this. So in particular, this is smooth. Of course, not inside X, but can be considered. And then, if you have this situation, then it's not so difficult to show there exists the so-called weight spectral sequence. E2PQ, which is HPYQ. So this exactly this meaning. And then QL, there's a Tate twist. And this converges to the cohomology of H plus Q, U, QL, no Tate twist. So this is just technique, but I show you one instance where one can understand this in a better way. Let's just say we have X a curve. And then we have U and X open. And then, of course, the complement Y is just a finite set of points. It is, of course, a smooth divisor even. And then you have the following, so H1U QL, then H1X QL. Okay, so I wanted to have this over the algebraic closure. Sorry. So QL, and you take this is injective. Then here you have H2 X bar with support in Y bar. And then here you have H2 X bar QL and 0. So, and then you have purity. This is actually isomorphic to the sum of these points. and then H0 y bar QL minus 1. So the weights, this is pure of weight 1, this is pure of weight 2, this is also pure of weight 2, and so this is mixed of weights 1 and 2. And this is a very particular case of the spectral sequence. So only a long exact sequence if you have a smooth divisor, but in general, sort of it's a combinatorial game to do this here. Okay, so the idea is to use this and according to my experience, I mean, this weight spectral sequence is basically, yeah, it's the best tool to understand the cohomology of arbitrary varieties. If it's smooth and proper, you have this purity, and otherwise it's mixed, and this weight spectral sequence tells you rather good information about this. Yeah?
I must be missing something very stupid about the spectral sequence. But so your indexing is that y1 is just are the single components yi, I guess, right? And
y1, yes.
right.
Yeah.
And so somehow for curves,
Yes.
phi consists completely of homology of
There you just have, yeah.
H0 of the point.
Right.
Nothing else.
Yeah, that's what happens here. And in general, you play sort of relative sequences like this.
That converging to the that converges to homology of U bar.
Yes. So you just do this somehow iteratively. So now for the proof of theorems 1 and 2 indication. So you have step 1 is via Hochschild-Serre spectral sequence. The kernel in consideration, so written in theorem 1 long time ago, is equal to the kernel of, you are just reduced to the second Galois cohomology of HD, so where D is the dimension of, D was the number of variables of the function field. Then I look at the L primary component, and then to the direct sum of H2 KV of exactly the same module.
Oh, sorry to interrupt again, but
Yes.
I guess the confusion is you need homology of X somewhere in there.
Okay. Y upper 0 is X. Y upper 0 is X. Yeah, by definition. Sorry, yes, I should have mentioned this. Okay. So this is basically this field here. This field has cohomological dimension D, and this is the top degree cohomology that you have. And basically, sort of, except for some problems with primes with real places and the prime P, this is actually isomorphic to the Galois cohomology I considered before. Okay. So and now this this here is Galois cohomology, but it's the limit. It's also Étale cohomology of this field, and it's the limit over all U. So let's say, so step 2, the following. So let's say F is K of V, yeah, for some variety. And then this is the limit over all open U and V. That's how you obtain, and then you take the Étale cohomology, U bar. QL mod ZL D plus, excuse me, D plus 1 is, this was wrong, D plus 1 here, D plus 1. Okay? So in other words, because the limit is the Étale cohomology of the function field, and the Étale cohomology of the function field is just the Galois cohomology. But now I have some Galois modules which I can understand, and where I can use the Hasse principle that I erased. So now I check on the weights. So the weight spectral sequence tells me at least in the curve case, you can see this. It has weight d, which is the dimension of u, d plus 1, and so on, until 2d. But also, from the Tate twist, you have to subtract minus 2d minus 2. Okay, and this means you have a big part where the weights are different from minus 2, and you have this perfect Hasse principle. So
Away from the characteristic.
L is away from the characteristic in the moment, yes. So you have sort of weights. So the Hasse principle, Galois cohomology, Hasse principle for weights smaller than minus 2. And you're only left with the top part. Top weight is minus 2. And there you really have to analyze. As I said, I mean, this one shows that actually, basically it could be difficult because you could have a torus, so to say, the torsion in a torus, which does not have a Hasse principle, but one can show that doesn't occur and one has the usual Hasse principle. So careful analysis. Analysis of tori. Okay. Now about the co-kernel. Yeah. Okay, look, then maybe I can just state the result. 5. So you have a Hasse principle for varieties over global fields. So again, K a global field and X over K smooth projective, smooth proper. And then Kato defined a complex, Kato complex of Gersten Bloch-August type. Type complex C21 of X. And okay, I do it with the infinite coefficient. So this starts with HD plus 2, the function field of X itself. Let's say QL mod ZL D plus 1. Then you go on with the D minus 1 dimensional points and so on. So I will explain this in a second. And then this goes on and it ends with the cohomology H2 K of X QL mod ZL1. And here xi are the points of dimension I. And K of X is the residue field of X. So in other words, these are global fields. And here we have the Brauer groups. And in general, you have exactly this situation that you have a function field of D variables. And these are exactly the groups which figure in the Hasse principle. So this is dimension D, here's D minus 1, and it's always D plus 2 and D plus 1, where D is the dimension of this function field. And then the theorem is the following. So, theorem 3. So in this case, a number field again. Same X connected, smooth projective. Then C21 over the global field embeds into the direct sum of the C21s of the XV, and XV is just X times KV, so just the base change to this here. That's the first situation, the first claim. And the second claim is that you have reside on the co-kernel. And this gives the information on the co-kernel for the previous Hasse principle. Is injective. And for co-kernel, this is another complex which I call C prime. One has the homology of this complex, which is a homological complex. So this is in degree. This is in degree 0 here, degree 0. And the top is degree D. So then this cohomology is 0 if A is different from 0, and QL mod ZL if A is 0. So in other words, if you take this as a replacement for the Brouwer group of a global field, Brouwer groups of the local fields, then you have a similar complex level situation that the co-kernel is at least quasi-isomorphic to QL mod ZL, yeah, as a complex. You have some injectivity, and the co-kernel is as a complex quasi-isomorphic to QL mod ZL. And if you want to check what this means for the co-kernel of the original map on the function field, this is the component in degree 0. So this means that you can write down this complex. Above, you can write down the complexes for all the xv's. And then you have this map that we considered in theorem 1 and 2. And the co-kernel sequence is exact. That's the information. So the co-kernel sequence is exact except for the last place. And it gives you an inductive procedure to calculate the co-kernel from the co-kernel of the smaller fields. That's the way one should look at it. And again, sort of theorem 4, resolution of singularities implies same for function field. Away from characteristic 0 and from the characteristic of the field. And over finite field, one can also do something in the characteristic P. Okay. Sorry for taking more time.
Questions, comments,
Maybe I just got a little bit lost at the end. Theorems 1 and 2 are just for function fields of positive characteristics? That's what?
One was for number fields,
one
and
was
2 was under the assumption of resolution. Yeah.
But the structure of the argument, if I understood, you were using this localization, vanishing of the kernel localization involving weight assumption.
Yes.
And using that together with the weight spectral sequence to get the Hasse principle.
Right.
Right? But that weight thing was for function fields, right?
That's right. But I mean, in this sequence, you have a bunch of function fields, always function fields.
Oh, yeah.
Now I write down the things. It gives me the opportunity. So, like the previous thing, so by Galois homology, the co-kernel. Once you have the, so in fact, the injectivity here is basically theorem 1 or 2. Okay? Because you have exactly the groups which we considered previously. And the co-kernel, C prime, is quasi-isomorphic to the following complex. So you take C00, I will tell in a minute. And then you can take the co-fixed module under the Galois group. So C00, this was the complex C21. So just imagine that you take a complex where here you start with 0, 0, okay, H2, 2. Then it goes back, and both degrees increase by 1 if you go that way. So in the end, you end by D, D, okay? And this co-kernel complex is isomorphic to this thing here. And now this is again exactly the same situation. This is, so to say, the top weight in the cohomology of, so this is not the H2, but it is this type of group with a D and then the cofix module. So top weight is 0, and that's all we have to consider. And it's a similar consideration. So basically the argument appears twice.
Other question?
Seems like you use resolution of singularities to get a good compactification.
Yes.
Is there some way to replace that by maybe compactifying via algebraic spaces or more general spaces?
Well, I mean, resolution for algebraic spaces is even more difficult. So I mean, there are considerations to do this with de Jong type of resolution. But I mean, so one has to be careful because in de Jong's resolution, you have a generic degree. And this, in general, if you cannot control this degree, then you, because this is really on torsion level. So you have L primary torsion, and if L divides the degree, then you get, you lose something. But I mean, there's Gabber's new result on that you can control the weight. I mean, this is not written up yet, but Shuji Saito and a student of mine, Moritz Kerz, are working using this to get this sort of from this weaker type of resolution. Yeah, but for the P, but that does not help for the P case because Gabber cannot treat the P case. Whereas here for the P, we get also I get it also for the P case or a finite field. Assuming
But the
resolution, of course.
So you need a very strong resolution. I mean, for every open, you must be able to compactify it in such a way that
In a cofinite family, that's right, that's right.
it's not enough to find once a good model and then.
No. One has to do it again and again in a cofinite family because we have to pass to the whole limit over all these U in some cofinite family, yes. But anyway, resolution in characteristic P should be done, so. Yes.
I'm puzzled by your conjecture about the injectivity.
Yes.
This is really a rational conjecture. You have to tensor with QL.
Yeah.
And I suppose in particular the Plato-Page exact sequence doesn't say anything about this.
No. So in the one really uses weights again in the case of a function field. So where one has this curve and cohomology of curves and so on, and uses really not just the statement of the Weil conjecture, but the proof of the Weil conjecture, because the Weil also says that the kernel is somehow controlled by, you have this U, which so U is something open then in a curve C over a finite field. And then call J the open immersion. And then one considers the cohomology of J lower star of F on C. And Dillon says that this is pure actually. This is a perverse cohomology, a perverse sheaf, so to say. And this is pure. And one would need an analog of that in the number field case also. So, I mean, one should have an analog somehow.
But not for any sheaf.
Pardon?
J lower star is pure for.
If F is pure, so if F was
if
pure,
F is pure,
yeah, I had F
J lower
pure.
star is pure.
Yeah, is it pure of, so in this case, if I look at the kernel is controlled by H2, so it's pure of the same weight plus 2. Yeah, so that's weight plus 2 should not be 0, so that's it.
The 2 comes from purity.
Yes,
Yeah.
yes, right.
But
And it would be a challenge to find a similar result, I mean, in a suitable analog over number fields. But I mean, there are no weights, so we can consider Iwasawa modules, but we do not have similar results, unfortunately.
So really for the reduction to the finite coefficients, you would only need the divisibility of the Galopo model.
Right, but this divisibility, I mean, it looks easier, but again, no way. I mean, I really wasted some years if I could
Maybe.
Could pass by
only
what,
the
yeah,
divisibility
yeah.
of the unramified.
Yeah,
The ramified.
yeah.
yeah, but, So in the conjecture, it's quite important that U be of dimension 1.
Yes,
Dimension 2, I could give you a comparison.
I'm sure, yes. This is really something about global fields. Yes.
Yeah.
Maybe no further question. Thank you again.